Hello.
Good afternoon, sir.
Good afternoon. Am I audible?
Yes, sir.
Okay. Okay. Good morning, everyone.
Now we will like to introduce our next resource person, Dr. Somnath Mukhopadhay, Department of Computer Science and Engineering, Assam University. Dr. Somnath Mukhopadhay is currently an assistant professor in the Department of Computer Science and Engineering at Assam University, Silchar, India. He is a former associate professor at the Department of Computer Application, Sikkim University, Gangtok, India. He completed his MTech and PhD degrees in Computer Science and Engineering at the University of Kalyani, India in 2011 and 2015 respectively. He has co-authored one book and more than 10 edited books to his credit. Some of the titles are Advances in Intelligent Computing, Algorithms in Machine Learning Paradigms, Methodologies and Application Issues of Evolutionary to Hybrid Framework, Multi-Objective Optimization, Evolutionary to Hybrid Framework, and Handbook of Research on Natural Computing for Optimization Problem, with some reputed publication venues. He also worked for several journals as a guest editor, such as Innovation in System and Software Engineering Springer, SN Computer Science Springer, International Journal of Advanced Intelligence Paradigm in the Science, International Journal of Ambient Computing and Intelligence, IGI Global, etc. He has published over 30 papers in various international journals and conference proceedings, as well as 6 chapters in edited volumes. His research interests include digital image processing, soft computing, optimization algorithms, and hyperspectral image processing. He is a senior member of IEEE, a fellow member of IETE, an ex-com member of IEEE CIS Kolkata, a member of IEEE Young Professionals, IEEE Geoscience and Remote Sensing Society, a life member of the Computer Society of India, and a former regional student coordinator of Region 2 Computer Society of India. To brief about our today's session, today we are going to learn about an introduction to optimization algorithm. We now hand over the session to Dr. Somnath Mukhopadhay. Please, sir.
Hello. Is it audible?
Yes, sir, you are audible.
Okay. Okay. Good morning, everyone. Madam, can I start the session?
Yes, yes. You can start, sir.
Thank you for the nice introduction.
Thank you, sir.
Let me now share my screen. Ma'am, it is visible?
Yes, sir. Visible.
Okay. 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 Thanks.
Okay, sir.
Okay. So, yes. So today I will be discussing about some introduction to
Any problem, sir?
the constraints, or if the optimization problem is a constraint optimization problem. So within the boundary of or maintaining the constraint.
Excuse me, sir. Sir, your screen is
Yes.
not visible.
My God. So previously it was visible.
Yes.
Still not visible.
No, sir.
Should I reshare?
Yes. You
Yes,
have
sir.
to reshare,
You
sir.
can.
So going to share option, share. I'm sharing my entire screen
Okay, sir.
and share. Now
And now it is visible, sir.
it's visible, right?
Yes, sir.
Yes, sir.
Okay, thank you. So we'll discuss about optimization, the definition, formal definition of optimization algorithm, some applications of it, and we'll discuss a single objective optimization algorithm using genetic algorithm. I will also discuss one multi-objective part of that is NSGA2 in this lecture. So an optimization algorithm will be used to find out the best solution or optimal solution out of all feasible solution. So the algorithm may handle constraints, and based on the constraints, we will find a feasible space, feasible solution space, and from that, out of feasible solution space, we'll find out the optimal one or the best one using any optimization algorithm. This is one example, a simple example. Let y is equal to fx. So we studied this during our higher secondary mathematics, that if y is equal to fx and if f dash x is 0 at any point, suppose the point is x star, then the optimal, I mean, it may be the maximum or minimum or the inflection point exists at that point. The inflection means where there is no maximum or minimum is present. So either we'll find the maximum or minimum at that point, or will not find any maximum or minimum at that point. So that is inflection point. So to further investigation, if we carry out, then we can say that first non-zero higher order derivative denoted by n, such that if n is an odd number, then x star is an inflection point. That means we can find out where there is no max or min is available or present. Or on the other case, we can find out that x star is a local optimum point. So either if n is odd, then we will find that we'll say that there is no max or min available or present. Or if n is even, then we'll say that x in that position there is the max or min is available. So further, if we go above on this, or further if we study, we can say that if the value of the derivative is positive, then x star is a local minimum point, and if x star is the derivative is negative, then at that position x star is a local maximum point. So using this methodology, using this principle, we can find out the max or min, or the point where there is no max or min available. So using this principle, the problem is we will only find out the local minima or local maxima. Also, if the search space is infinite, then also this algorithm is not applicable. So this algorithm is a solution for finding solutions where the search space is very small. Also, the search space has to be continuous, otherwise we will not be able to find the solution. So the optimization algorithm can be solved, an optimization problem can be solved by using derivatives, or by using without using derivatives. So by using derivative, one can solve the problem using gradient descent algorithm. So hope everyone may have idea about gradient descent algorithm, where we find out the partial derivatives to find out the next max or min position using the gradient of the particular function. So So there is a whole branch of mathematics concerned with this with computing gradients. It is also known as differential calculus. The idea is to just, if I can use the paint, is it also visible? Madam, is it also visible? The paint?
Yes, sir, visible, sir.
Okay. So if I consider xy axis like this, if a function looks like this, a continuous function, which is also, the function is non-convex. The problem, function is not convex. A function is convex when the function is a straight line. If the function has a curvature, then the function is not convex. So we cannot also solve a problem. I mean, if the fx is of this of this structure, then x, and then so the x is increasing. Is in here, that means this is our del x, and the corresponding y is increased this amount. So this is del y. So this is the gradient. Actually, this is the gradient, or this is the change of y with respect to change of x. So del f x with respect to del x equals to f of x plus f of x plus the amount of change of x minus fx divided by del x. So this is the derivative, or this is the gradient, we can say, by which we can also determine the gradient. If I want to find out a solution, I mean the optimal solution, it will be local optima, of course. So this, in this case, if my df dx, if my df dx is, it's not, if my df dx is greater than 0, that means the slope is from left to right. If the slope is like this, that means my df dx is greater than 0, it's a positive gradient. Then fx increases. If fx is increases with when x is also increasing, that means we have to decrease x to find out the minimum value of this function. So, and on the other case, if df dx is greater than 0 and fx is, suppose the gradient is, I mean the slope is like this way, then if df dx is greater than 0 and fx is increasing, suppose fx is decreasing as x is increasing, in that case we have to increase x to find out the minimum value of that function. If df dx is greater than 0 but fx is at a maximum or minimum, so we do not change the x. So this is the principle of the gradient descent algorithm. So we can summarize this by using, so the amount of x we need to change is equals to, so the x new value minus x old value is equal to some eta of, this is the learning rate, so df dx. So this is the algorithm for finding the gradient descent, and by which we can find out the optimal solution, or I mean the local optimal solution using gradient descent. This way we can find out the optimal solution of problems which are either the equation is monotonically increasing or the function is function is monotonically decreasing. But if the function has a curvature like this, so where if x is increasing, fx may decrease or fx may increase, or in that case, so we'll find out only the local optima in this case. In that case, so by using gradient descent, we cannot find out the global optimal solution, because suppose if we consider this function here, there are two basins. So if I'm interested to find out the minimum value, so there is one minimum value, there is one minimum value. So among these two, this one is the global minimum and this is the local minimum. So by using this principle, by using this algorithm, gradient descent, we cannot find out the global best or global minimum of this. Also, this is one limitation of this gradient descent algorithm, because if there are many basins, or if there are many local optima, so finding out the global optima may require several iteration or several trial to find out that. So also this is one limitation of this gradient descent algorithm. It works perfectly well when the function is non-convex. Also, if the function is a discrete function, if it is non-continuous or discontinuous, then gradient descent is also not applicable. This gradient descent algorithm can be used for finding out one application of this algorithm can be finding out the regression problem, where if I have some data points, populated like this, if I want to find out the best fit line which perfectly maps these all points, then this gradient descent algorithm can be used here to find out this, because there can be many best fit lines. So which line is best to describe these data points is a difficult problem. Suppose if we consider that if the best fit line going through the origin, that means if the equation of the straight line is y is equal to mx plus c, if the straight line goes through the origin, that means c is 0, and m is my gradient, m will be my gradient df dx or dy dx, whatever. So by using this different x value, we will find out different m value. So by finding different m value, so that m we need, for which I mean that slope we need, for which we will find out the best best fit line, because if the cost function of this gradient is of this problem, this regression problem, this is a linear regression problem. If the best fit line has a gradient like m star, so that m star we need to find out, for which we'll find the less error, because if the equation of the cost function is jm, suppose, equals to, it will be the error, that is y hat minus y whole square. So the y hat is the predicted predicted value, and y is the actual value. The difference is the error. So we have to find out such a m for which this error is minimum. So we can solve this problem by using, suppose the aim is here and this is my jm, the cost function. So if I consider many different m value, we'll find out the corresponding error, the corresponding difference between the actual and predicted output. If we plot this, it may look like this. So here there is the minimum error. So suppose the m value is 5. So for the m value 5, this fx function, the jm function, has a minimum here. So that means the error is here. So this is the error function. This is the cost function. So we can solve this by using gradient descent. How? If we start this algorithm, If we start this algorithm, we may find out a convergence theorem here. Suppose the convergence theorem is like this. This is the convergence theorem. Suppose the convergence theorem is suppose. So we have to find out such a m for which the error is minimum. So m dash, the updated m equals to the old m minus dm djm of course, this is the cost function, by delta m with some learning rate eta. So in this case, we will find out, or we will try with different m value, and we will find out which one gives the best solution. If we start our search process from here, so here we'll see that the gradient is, the slope is here negative. So in that case, so as m increases, the jm is decreasing. So from our previous knowledge, we can see that. So m dash will be m minus, the gradient is negative, so some negative value, into here the learning rate eta is a small value, some small value. So it will be actually m plus some small value. So that means we have to increase the value of m. So m updated will be the old m plus some small value. If we start my algorithm, I mean the search algorithm, randomly from suppose this position. So here we can see that m dash will be minus the gradient, suppose this is g, into some small value eta. So here m minus, so here the gradient is what? The gradient is positive. So gradient is from left to right, the gradient is increasing. That means it is a positive value. So gradient is increasing, that means here it is a positive, and the learning rate is a small value. So that means m minus small value. So in that case, what we need to do, we have to decrease the value of m. So the updated m from this position, what we have to do, we have to go back this way. So that way, this way we can find out the corresponding m value, for which we'll get the jm minimum. When jm is minimum, that means the regression problem will be solved by this way. So this is one algorithm which is completely derivative based. So derivative based algorithm which we can use for finding out or solving a regression problem when the data points are populated in a, or I mean, so this is one example by which we can find out a local minima, not global minima, because here the problem is look like this, then we can find out global minimum. But when the problem has curvature like this, we cannot find out the global optimal solution by using derivative based approach. Also, this has one more challenges or the limitation, that is, it cannot solve a problem or a function which is discontinuous. So to solve such problems, we need to go for some derivative free algorithm. So the derivative free optimization algorithm has the advantage that it can solve or it can find out global optimal solution. It guarantees that. It can also solve non-convex problem. That means when there are many local optima, and out of which one will be the global optima. Also, it has the advantage, or it has the strength to find out the solving a discontinuous fx like that. So on that path, we will study here, we will discuss here one algorithm which is a very powerful algorithm for search and optimization, that is genetic algorithm. It was proposed. It was originally developed by John Holland in 1975, and but it was proposed during the late 80s by you know the Goldberg. So this algorithm is very powerful. This algorithm is very has the capability, has the strength to solve any optimization problem, which can find out global optimal solution. So it follows the principle of natural genetic system. It is inspired by biological evolution process. It uses the concept of natural selection. The algorithm starts with randomized chromosome encoding. Then the solutions are inherited to the child chromosomes, child solutions. It follows survival of the fittest, that principle. So let us move ahead to discuss about this algorithm. This algorithm is very much powerful in solving any NP-hard problem. This problem can be solve any problem using in a uh, in deterministic time. That means the if the NP-hard problem which is really difficult to solve in polynomial time, but genetic algorithm guarantees that it can find out the optimal solution, the global optimal solution in polynomial time. But sometime it may stuck in suboptimal solution. So that is there. So if we consider a problem like traveling and salesman problem, where one salesman is there who traveling many cities exactly once, and if we want to find out what is the minimum cost by which he can travel all the different cities, if we even consider only 3 cities, so there can be 9 different paths, factorial 3. So this is a NP-hard problem. If we consider 100 cities, so the different possible paths of visiting 100 cities will be factorial 100. Even it is really a difficult problem to find out the factorial 100. So this is a NP-hard problem which can be we cannot solve this problem by any deterministic algorithm in polynomial time. So that is impossible for our latest computer also to solve this problem in polynomial time. So here we can, what guarantees that genetic algorithm or any search and any optimization algorithm, what it guarantees that it can solve any such problem, any NP-hard problem in polynomial time with very close to the optimal solution. It provides a very close to optimal solution. So this GA can be used when the problem is NP-hard, which cannot be solved in polynomial time. Then there we can use genetic algorithm or any optimization algorithm, particle sum optimization algorithm or differential equation, and there are many algorithms which can be used for such purpose. But genetic algorithm is very classical, or you can say this is mother of all optimization algorithm, which so when the problem can be modeled as an optimization problem, we can use genetic algorithm. It can efficiently searches for global optima when multiple optima exist or present. That means when there are many local optimas, there we can use. Parallel implementation is easy, but the part of there are some component of algorithm which can which can be implemented or which can run in parallel with other other part of the algorithms. So genetic algorithm here from this diagram we can see if this black line, if this is a problem class, if the x-axis represents the problem class and the y-axis represents the efficiency, we can see that one specialized algorithm is performing best for a particular problem. Suppose in this position, in this P, the one specialized algorithm is performing very best. But genetic algorithm on the upper of that, above of that, genetic algorithm is performing good for all the different problems represented in the x-axis. And for a particular problem, maybe for a particular problem P, genetic algorithm is little, has little less efficiency, or the specialized algorithm is performing better compared to, or it outperforms the genetic algorithm. But for a set of problems, the genetic algorithm is performing best. So that is the beauty of this algorithm, which can work for many problems, many kind of problems, or it can be used for several different problems. So that is the strength of this algorithm. So one specialized algorithm may perform best for a special problem, for a particular problem, but genetic algorithm has a good result, or has a good performance over a wide range of problems. So it has these features. It is a search and optimization technique. It uses this technique. It follows principle of evolution. The fittest algorithm will, the fittest solution will survive, and the which are not will be, will abolish, will not survive further in the further generation. It starts with encoding the parameter set, the solution set. It searches from a population of point. It uses probabilistic transition rules. We'll discuss these points. So GA is inspired from this algorithm, inspired from nature. So there will be always correlation, or there is always inspiration from nature for working this algorithm. So it has genes which represents individual individual solution. Not gene is not the solution actually. The set of genes is the solution, which is known as chromosome. The part chromosome is gene, which is the candidate solution, and which gets better and better after generation by generation. Which this algorithm has some stochastic operations, which are random algorithms, which is selection. The solution which is best, or which has better fitness, will survive. Other solutions which are not such so best will be not carry forwarded to the next iterations or generation. It has a crossover operation, which is reproduction from parent to child solution generation, which is actually known as exploitation in optimization theory. So exploitation means what you have in your hand, just use those things, or recombine them to generate new solutions, which is exploitation. And there is another operator, which is mutation, which is actually searching new search area, searching new unexplored search area. That is known as exploration. So exploitation and exploration, two different concepts which is used in optimization algorithms. So how it works? It starts with some initial population which is randomly encoded. Then the fitness of that of those chromosomes, or those solutions, are determined, calculated. If we are satisfied with that fitness, we can terminate. Otherwise, we go to the next phase to select the best chromosomes, best solutions, and we create a mating pool. From the mating pool, we perform the crossover operation, we perform mutation operation, and again we evaluate the fitness, and this way the cycle repeats itself to generate new and new solutions. And whenever we find that solution, the solution what we have got so far is satisfactory, we will terminate the process. So this is the algorithm. This is the overall algorithm of this genetic algorithm, which will be used to find out the solution. So the first phase is chromosome encoding. It can be binary encoded genetic algorithm. It can be real coded genetic algorithm. So if we use binary coded genetic algorithm, then the solution or the chromosome is represented using zeros and ones, and by the several solutions where we from where the chromosomes are encoded, or the solution set, several solution set is known as population. So population size is usually user supplied. So common practice is to choose the initial population randomly. Suppose this is the problem, if we consider, so fx equals to some function where x is defined in a particular range. So if we use binary coded genetic algorithm, so here x can be represented by using some bits. So here the value of x is in between 0 to 8. So a simple thought process says that it is a very simple problem, because optimize fx equals to x into 8 minus x, where x is in the range of 0 to 8. So if we put different values of x in fx, we'll find out the fx value, and from where we can find out which fx is maximum, and that is the optimal solution. So here the problem becomes difficult when if we take because here only there are 9 x values. So if you just f of 0, f of 1, f of 2, f of 8, if we compute, we can easily solve this problem. But if this problem becomes difficult, if we consider the x is up to suppose 4 decimal places, so then it becomes really a difficult problem. Or in other words, we can say the range of x becomes extremely large. That means, or you can say the range becomes infinite, because if x is considered up to 4 decimal places, then the first value is 0 and the second value will be 0.0001, and the next value will be 0.0002. So this way it has a infinite number of x values in between 0 to 8. So this becomes a difficult problem. So we cannot solve by any direct approach or any deterministic algorithm. So here genetic algorithm can be used to solve this problem. So we can represent the value of x by using binary bits, which where the x values can be represented by using 8 bits. So if we represent the x value using 8 bits, then 8 bit can represent minimum 0 value and maximum 255. So this 0 to 255 which we encoded has to be converted to 0 to 8. So this can be easily done. So one value which is in 0 to 255, we have to convert this to 0 to 8. So this can be used by this. So if one randomly encoded chromosome looks like this, 100111010, the corresponding decimal value is 154. So now with this 154 value is converted to a range of 0 to 8, which is nothing but 4.8313. So this x value now, so different chromosomes are encoded, which is kept inside this population. Suppose the value of the population is 4, so that means there are 4 chromosomes, and the corresponding decimal values of this is this. I mean, not the decimal value, the value which is in the range of 0 to 8. So this is the suppose this is the string, which is the chromosome, which is converted to in the range of 0 to 8, which is 4.8, like that. So these values are, the corresponding x value. If we put these different x values in the fx value, we'll get this kind of fx value. So these fx values are nothing but the fitness of the different solutions, different chromosomes. So among these, we have calculated the fitness value, which we now ready to go for selection operation. Selection is actually used for finding out the best solution, the survival of the fittest, just following this principle. So on that, the good solutions will survive, and bad solutions will be destroyed or will be removed, will not be able to survive. That is the thing. So there are many selection algorithms, but these are popular, these are classical, which we can use for selecting the best solution. So one relative selection algorithm is there, which actually selects which actually ranks the best solutions in terms of their fitness value. So suppose this is one wheel. So the wheel has several partition, and the partition amount is actually the cumulative sum of these fitness values. Suppose the cumulative sum of these values are 50. So out of 50, 15.30 is the percentage of amount of occupancy in this wheel. So this way we can plot or we can map chromosome 1, 2, 3, 4 here, and then there is a pointer which is actually pointing to this wheel. Now if we spin this wheel, and when it stops, the pointer where it will point to will be the chromosome which will survive or which will win this test of selection. So suppose spin 1, chromosome 2 is selected, from chromosome spin 2, so the other chromosomes are selected. So this way, so the thing to remember here is, or to notice here is, the thing is completely random. So nothing is here which is manual. So the thing is random. So maybe one chromosome, suppose chromosome 1 will be selected many times, is possible. So this way, this mating pool is generated. So the disadvantage of this relative selection is, or it is not disadvantage, it is a natural process, that the worst chromosome can also be selected. That is the thing which can occur here, which can happen here. So because that is natural. In our natural real life also, not always that the best solutions will only exist or will only survive. Some solutions which are not so good or not so fit will also survive in our nature. So this way this solid wheel works, and this way this selects the chromosomes which are having better fitness value. So here this is the advantage, and okay, so this thing can be or can be avoided by different selection operator, which is, or selection algorithm, which is two-dimensional selection, which is which guarantees that the worst chromosome will not be selected. Here the worst chromosome can be selected. There is a chance of that. Here the worst chromosome will not be selected by any chance. That is in the tournament selection, which is actually a knockout type thing, knockout game, where randomly any 2 chromosomes or any 3 chromosomes are selected, and from that the best one is selected to go for the mating pool. So this way, tournament selection always guarantees that the worst chromosome will not be selected by any chance. So the next operator, or the next thing is, crossover operation, which is actually used for, which is actually exploitation operation, which uses the existing chromosomes to generate new chromosomes. So parents generate child chromosomes. So there are many different crossover operation. This operation is probabilistic. That means not always crossover happens, but it has higher probability to happen. So this is one single point crossover example diagrammatically, where there are two different chromosomes, two different parents. If we use single point crossover, one point randomly, selected, and from there their information is exchanged. This way, this algorithm can generate child chromosomes from the parent chromosomes. So there can be a uniform crossover method which uses a mask of zeros and ones. Where there is a one, we can exchange the genetic information, or where there is a zero, we will not exchange. So this, using this principle, we can make one crossover operation. So mutation is the last phase or the last operation which we perform in genetic algorithm, which finds the mm, which explores the unexplored area. So so this is the strength of genetic algorithm. It can find out, or it can searches the unexplored search area where the global optimal solution may present, but by using only crossover, we cannot find out, or we cannot reach that unexplored area. So, so mutation is a very, very powerful algorithm. Even in today's research, when we hybridize, suppose, genetic algorithm with particle swarm optimization algorithm, so we always consider mutation as a powerful tool for exploration. Because in particle swarm optimization algorithm also, there is the PSO has a very good strength of finding out local optimal solutions, or in a best solution in a particular region, in a particular topology. But to find out the solutions, the search area which is unexplored, the mutation operation is very much useful to do so. So when we hybridize PSO with genetic algorithm, we consider the some part of part PSO for exploitation, and of course all the mutation part of genetic algorithm to find out the to do the exploration of that. So this is a powerful tool for finding out unexplored area, to find out unexplored search areas. So how it happens? It also mm, used to avoid local optimal solutions, because sometimes the solutions, the search algorithm is stuck in local optima, but by using mutation we can overcome this. We can go beyond the current search space, current search area. So it's how it happens. It happens by using random alteration in the genetic structure. I mean the chromosome. It introduces the genetic diversity in the population. It explores new search areas, and just mutation means negation of the bit, means if we make 0 into 1 or 1 into 0, it generates, the mutation is done. It is also a probabilistic operation, and although it has a less probability, maybe below 5-6% amount of time mutation happens. So this is one example of the mutation algorithm. So we how it happens? So we generate some random number. Suppose the percentage or the probability. Sorry. suppose the probability we consider for mutation operation is 10%. Now, if we generate one random number and between 0 to 1, if the random number is suppose 0.0 to 0.1, then we perform mutation. Otherwise, from 0.1 to the value 1, we do not perform mutation. So this way, so for every single bit we check for the probability and we decide whether to perform or not in this algorithm. Okay, so the parameter set, these are the parameters which are user supplied. Population size, the chromosome length, the probability of the crossover, probability of mutation, the termination criteria, termination in convergence, when to stop the algorithm running, that is the termination criteria. So those things are user supplied, but these are typically, in this algorithm, these are used, but for a general case, we can consider chromosome length, population length, 30, chromosome length 20 to 40, crossover probability 80 and above, mutation probability 10% or less. This way, we can set the different parameter values of the algorithm. So how we can terminate? We can observe how when we are finding out or we are converging towards the optimal solutions. So if we always observe in a window of suppose 10 iteration, so if we compute the best solution of that, and when we observe that there is no change on that, we can terminate. Otherwise, we will continue, or otherwise we can only iterate it for 200 or 300 iteration. In that case also we'll find out the optimal solutions. So there is a little bit more, there is elitism. So elitism means the elite solutions are given some preference, or they are saved because they should not be destroyed or altered in the next iteration. So the solutions which is find out which is based at current generation. So what do? We preserve that solution outside the population, and at the next iteration we also find out the host chromosome, and if we compare these two, the best of previous and the host of current, and if the host of current is better than the best of previous one, we survive. We survive the host of current iteration. Otherwise, the best of previous replaces the host of current iteration. So this is the elitism model of genetic algorithm. So this is all about single objective genetic algorithm, which can be used to solve any single objective optimization algorithm by this principle. So now I will move forward to discuss about multi-objective approach of this algorithm only. So when there are more than one conflicting objective, suppose we want to buy a car. Sorry, this is BUY. If we want to buy a car, suppose Mercedes-Benz or Tata Nano. So which car to buy? So these two car has their own beauty. Mercedes-Benz has some beauty. Tata Nano also has some advantage or disadvantage. So what do we need to consider when we buy a car? Whether the comfort or the cost, or there may be many other parameters. So if we consider comfort, Mercedes-Benz is always better solution. If we consider cost, Tata Nano is better compared to Mercedes-Benz, because Tata Nano has a lower cost compared to Mercedes-Benz. So there may be many parameters actually in our real life problems, in our real life, which we cannot, there is every reason to consider those parameters before doing any, you know, mm, before deciding any or before solving any real world problem. So when there are more than one conflicting objectives, we have to use multi-objective optimization problem. And what is conflicting? Conflicting means somehow one objective function is orthogonal to the other one. That means if we consider cost, then we have to compromise on comfort. If we do not consider, I mean, if we want to concentrate or focus on my comfort level, then I should not think about cost. So these are somehow this way they are conflicting. So now which solution is best, nano or bench, Mercedes bench? So we cannot decide which actually which solution is best among these two solutions. So in this kind of problem, real world problem, we have to consider or we have to go for some multi-objective optimization, algorithm. So improvement in one objective causes degradation in another objective. So most of the real world problems are multi-objective in nature. So suppose if we consider this, algorithm, this example. So in the x-axis there is the economy level and y-axis there is the time taken. So in x-axis there are some transport system, transport type, and in y-axis there time taken. So starting from one person standing to a rocket, so their economy level is different. If we go somewhere by walking, then there is hardly any cost involved. But if we use a cycle, then there will be some cost involved, and more cost using a horse, more cost using a bike, a two-wheeler, more cost in a four-wheeler, more cost in a helicopter, and so on and so on. So in this way, the economy level is increasing towards the x-axis, and the time taken is decreasing. So these two objective functions, the time and the economy, are conflicting in nature. So here in this solution space, there are many solutions, and we cannot choose or we cannot say that this solution is the best solution, because one solution has lower economy level, or higher economy level. Also, in that sense, it takes less time. So one solution is we cannot compare two solutions, because horse, and if we consider horse and bike, horse will go somewhere in less time compared to higher time compared to a bike. So they are not comparable actually. They are not comparable. When two solutions are fixed or have a same value for a particular fitness function, then we can compare. Since if we consider these two cars, so they have same economy level, but one car is taking higher time. So in that case, we can see this green color arrow, this car is a better solution compared to this. But we cannot compare this car with this helicopter, because this helicopter is costly than the car. But on the other way, this which is costly is a disadvantage, but it is taking less time. So this, in that sense, we cannot compare them. So this is actually known as dominance principle. So when two solutions cannot dominate each other, then we cannot decide also that which one is best or which one is poor. So this is mathematically defined, formally defined. in some single objective optimization problem, one function is optimized with some constraints, with some conditions, and in case of multi-objective optimization problem, there will be many functions f1, f2, f3, and we have to optimize these all functions simultaneously with some constraints. So this is one example of a multi-objective optimization problem where we have to minimize x square, one function, suppose f1x, and another function which is f2x, which is actually x minus 2 whole square, where the value of x is given in a particular range. So here we can see when the value of x is in the range of 0, 1, 2, then only when the value of x is 2, the x square value is 4 and x minus 2's value is 0. When the x value is 1, the corresponding x square value is 1 and x minus 2 whole square value is 1. And when x value is 0, this is 0, 4. So in these three cases, we can see they are incomparable. They are not comparable. For 0, for 1, for 2, somewhere x is, these three values are the minimum value. But when the value of x is x equals to 4, we can see the value of x square is 16 and x minus 2 values. So which solution is best, or which solution is should we consider as the better solution when x is 2 or when x is 4? Because 4 is less than 16, 0 is less than 16. So of course the value of 2 is value of x when it is 2, it outperforms, or which actually dominates the value of x is 4. But when the value of x is 2, the x square value is 4, 0. So when value of x is 1, so we cannot compare the value of 1 when x equals to 1 and when x equals to 2, we cannot compare. They are incomparable. And these three solutions are actually non-dominated solutions. So no solutions can dominate each other. But if we consider x equals to minus 1, we can see the first fitness function value is 1 and 9. So this perfectly worse solution than when x equals to 0. So here the Pareto front means a set of solutions which are non-dominated in nature. So that is known as Pareto optimal front. So this is a scaper study. So here some terminology that the value of x is plotted. That space is known as variable space or genotype space, where the objective is the fitness values are plotted, that is known as phenotype space. So in scaper study, this is given. So x here is the variable, it is genotype, and x square and x minus 2, these are the fitness function, which is the phenotype, the objective space. So multiple distinctions from single objective optimization, multiple conflicting objectives as opposed to single one. So in case of single objective solution, we can easily compare two solutions. But in case of multi-objective solutions, we cannot compare. So this is the, in left hand side, that is the decision space. Right hand side, that is the objective space. So in this left hand side, the x values are plotted, and that x value is applied to some fx, and we find out the corresponding objective space. And from where, if it is a minimization problem where f1x and f2x both are to minimize, then this area, this red colored area, is the Pareto optimal. Here there is the Pareto. So the solutions which are non-dominated are existing. So what is dominance? So in case of single objective, one solution, suppose I have bought a car which cost 6 lakh. You have bought a car which cost 8 lakh. So which car is best? So which has less price, less cost. So 6 lakhs car wins. So this is very simple. But if it is considering another parameter, suppose the comfort or the mileage or the ground clearance, or the music system, there can be many parameters which we need to consider when we buy a car. So if we consider many other parameters, so one car which has less cost will be also having less comfort. One car which is having higher cost will be having more cost. More comfort. So we cannot compare. So 6 lakhs, if the comfort percentage is 60%, one car which is 10 lakh will be, suppose the comfort percentage is 90%. So they are not. So no solution is actually dominating the other. But there is a principle by which we can say that this solution x1 dominates other solution x2 when if we can find out that that if every objective of x1, I mean suppose one objective here is you consider cost, and another is suppose the time. So if we go from Silchar to Durgapur by train, it will take some time of 40 hours. And if I go by using suppose flight, it will take some 2 hours of time. So these two solutions, solution 1 is train, solution 2 is flight. So these two solutions are actually incomparable. They cannot be compared or able to compare because they are having different cost involved. So both the solutions are best solutions. If someone is going by train is not a bad solution. But if I go by Kanchenjunga Express and you are going by suppose some other train, I don't know other train, suppose some other train. So if both are going by same train, same price, but one train is reaching there before the other or in advance, then one train will be winner in this case. But so they will be only comparable when there one solution is fixed and other are different. So in one case, one solution is better than the other solution for all I, so for all values of the fitness. And there is a particular I for which this solution is strictly dominating the other, strictly better than the other. Then we can say the solution x1 is better than or dominates the solution x2. So this way we can define, or this way we can sort two solutions. So this is one example. So here the blue, if this is a minimization problem in xy axis, the blue ball dominates the red ball because blue ball has a less x value, blue ball has a less y value. So it strictly dominates the red ball. But similarly, the green dominates. This green is actually inside this position. The green dominates blue ball because the green has a less x value, green has a less y value. But blue is not dominating the gray one. Blue is not dominating the gray one because blue has a less y value compared to these gray balls. And gray can also not dominate the blue one because the gray has a less x value. So in one, when you are considering x value, one solution is better, and when you are considering y value, the one solution is better, other solution is better. So they are not comparable. They are both are non-dominating in nature. So few more things. Solution is Pareto optimal if no solution dominates it. Set of all Pareto optimal solutions points in variable space is called Pareto set. set of all Pareto objectives is called Pareto front. Hope you have understood this thing. So this is a minimization problem. We can see these white balls is actually a poor solutions compared to these blue ones. And these blue ones, when they are joined, because these blue and these blue are actually non-dominated in nature, because this blue has less y value, and this and this blue has a less x value. So these two blue balls are non-dominating each other, and when they are joined, they generate a Pareto optimal front. So this is the concept. So if the problem is a mean problem, then this position, this area is actually Pareto optimal. When this is a problem with max mean, and that means F1 is to maximize, F2 is to minimize. I mean min max. This is min max. This is max min. So in different cases, different areas are Pareto optimal. So one problem is minimization or maximization can also be considered as a problem of minimization if we just invert that. I mean, this is a duality. One problem, fx to maximize means 1 by fx to minimize, or minus fx to minimize. This is a duality of these things. So what is the goal of this multi-objective optimization algorithm? So we need a solution space. We need a Pareto optimal front, which will be, close to the original solution, close to the best solution, or the solution which you could find out by using mathematics. So that is the optimal solution. So we always try to reach as close as to that solution, because by computing power, by computing by some computation, or by using any algorithm, we can only try to reach to the best solutions. But mathematically, we will always have a different, have a target to achieve that. So the convergence to the true Pareto optimal front is our one goal. So try, if your problem is a minimization problem, so min, so this area is the best solution, because this is the 0 position. So trying to just going near to that 0 position, or this origin, is the target. So that is known as convergence. So practically as close as possible Pareto optimal within the stipulated time. So that is one objective. That is one goal. Another is well diverse. So well diversity is required because many different person may have different kind of choice. So one can choose Tata Nano as a best solution. One can choose Swift Desire. One can choose Mercedes Benz. So different people will have their own choice of buying the car, and all these no one is actually dominating other. So as wide as possible is another objective. So cover the whole spectrum of Pareto optimal front. So diversity and convergence, these are two objectives in optimization when we are solving a multi-objective optimization problem. So these things, so this is a classical approach. So these are not really used in today's this diverse problem area. So since time is less, I am skipping this part. So there are many multi-objective version of genetic algorithm, starting from population based, archive based, the size of the working principle, whether it is microgenetic or macrogenetic. When micro means when the solutions subspace is small, it is microgenetic. When the subspace is small, max in large, it is macrogenetic. This is archive-based genetic algorithm. So there are many kind of MOGA available, but MOGAs a lot. There is many algorithms, but we are discussing in today's class is NSGA2, non-dominated sorting genetic algorithm, which is second part of non-dominated sorting genetic algorithm, NSGA2. In the first part, there was no the elitism version was not there, and it was not so fast also. So it was proposed by Professor Dev in 2002. It has only this publication has more than 53,000 citation. It is a population-based algorithm. It uses large search space. It works in generations, and it uses elitism model. So how it works? It starts with some PT, that is the parent chromosome. From this parent chromosome, we generate some QT, a duplicate of that, not exactly duplicate, by using crossover, by using selection, by using crossover, by using mutation, we generate this QT, and this PT and QT are merged. If PT is having size 20, so QT is also generated, which will be having size 20. So 40 size chromosomes is generated. So out of these 40 chromosomes, we find the best 20 solutions. So some solutions which will be rejected actually, which will be not considered for further. So PT and QT is union, and they make RT. From RT we generate PT plus 1, the next iteration solution. So how this is done? We perform here some sorting. So non-dominated sorting. So we actually rank those solutions, and some solutions, suppose some solutions, one solution which is in same rank, suppose rank 1 solution. So there will be some solutions which are rank 1, which some solutions which are just like this, or better this one. You consider this, suppose this is a solutions search space. So this 1, 6 and 2, these solutions are actually non-dominated. They are coming under front 1 solution. Some solutions, suppose 5, 8 and 3 are coming into front 2 solutions, because they are also non-dominated, but all front 1 solutions are actually dominating these 3 solutions. So front 1 dominates front 2 solutions dominates front 3. This way they are ranked. But which solution is best, 1 or 6? So to do so, so sorting can be done by for using just for selection, and another parameter which will be used for selection is actually crowding distance. The domination count. So there will be solutions. So we'll count the solution 1, this solution, how many solutions are dominating this one. So that will be the
No
domination.
slides are there.
Sir, please share your screen once again. It is now visible, sir.
Just is it okay?
Yes, sir.
Okay. So So we will count okay. So we are performing non-dominated sorting and then finding out crowding distance to calculate the rank of the solutions. So after the sorting algorithm, when there are suppose f1, f2, f3, if there are many functions which we need to optimize. So just by using sorting on 2, 3 fitness functions is really difficult to handle. So that's why this NSD2 algorithm has in this algorithm Kullan has proposed this in his the non-dominated sorting algorithm. So by which we can rank. So after the ranking, so in a particular rank, which solutions are best or which solutions are poor. To do so, we calculate the crowding distance function. Crowding distance of individual solutions. The crowding distance is actually a parameter to preserve diversity. So rank is, I mean, non-dominated sorting is used to, preserve neighborhood solutions. So this way, their crowding distance is calculated. I can tell you the formula of crowding distance function if I have time.
Sir,
So the
hello.
yes,
Sir, your screen is not visible.
what is
Voice
happening
is, voice is clear, but the screen is not visible.
now?
Yes, sir.
Yes, sir.
Okay, the value of the crowding distance of the D1 equals to the boundary solutions are having some are given some infinite crowding distance value. Suppose you have 5 chromosomes 1, 2, 3, 4, 5 and their corresponding F1 and F3 value corresponding F1 and F2 values. Suppose there are two different fitness functions. So they are sorted, and when something is sorted, you will see that in the boundary there are some max and min values. So those two values are kept intact or untouched to preserve the diversity, and the in between solutions are used to calculate the crowding distance. Suppose there are 1, 2, 3, 4, 5. These 4, 5. These are the different chromosomes. Suppose after sorting based on their fitness value, suppose by F1 and F2, these two are fitness value. So by using F1 value, we'll have a sorted chromosome. By using this will be also sorted chromosome. So here we will find the boundary solutions. So these solutions, for these solutions, we actually consider their crowding distance value infinite, and the in between solutions are considered for to calculate the fitness value. And initially, they are suppose this is D2 and D5. Suppose the boundary solution. Suppose this is D2 and D5. Or it's chromosome 2 and chromosome 5. So D1, D3 and D4 initially we will calculate, we'll assume their crowding distance value 0, and now from this assumption we'll calculate the crowding distance value of D1 equals to what? D1 plus the previous value F1, this is the fitness F1 4. Suppose the two neighboring solution is 4 and 5. So 1 is present between 4 and 5. Suppose. So F1 4 minus, so F1 5 by the fitness of F1 max and fitness of F1 min. So by using this formula or by this function, we can calculate the updated crowding distance for D1. So by this way, we can calculate the fitness values, crowding distance values for all the chromosomes. So if you have any further discussion on this, you can email me. Today I do not have much time. So this is the thing. Crowding distance is infinite is considered for the boundary solutions. For others, the crowding distance is calculated. So how the selection is done? So if two solutions are, if solution I dominates Ij, when their ranking is, when the rank of I is less than ranking of J, that means I dominates J. But in that case, when the rank is same, then how we will calculate their performance? Which one is best? The solution which is best, for which the crowding distance is higher. So more the crowding distance, better the solution. So this is the principle of this. So how we can, and the crossover mutation thing is same as we started for single objective genetic algorithm. So performance actually we can use hypervolume for measuring both convergence and diversity. When it is a single dimensional single fitness value, then we calculate the distance. When it is a two-dimensional, we calculate the area. When it is more than two-dimensional, we calculate the volume. So this is the one example, and by which the hypervolume can be used for measuring convergence and diversity. So more the hypervolume, more the better the solution. To solution 1 and 2, one car designed by Tata and one car designed by Mercedes. So which solution is best? The solution which has higher hypervolume or higher area will be the best one. So there are so there are some advantage of evolutionary algorithms. It do not need derivatives. It is simple to implement. It's flexible. So we have many things, many advantages of this. And still research is going on working on single objective, multi-objective, many objectives. So when there are 30, 40, 50 objective functions, it's still difficult to actually sort those solutions because somehow one solution is somehow better than some other solution for a particular fitness value. So in that case, actually no solutions is actually neither better than other nor poor than other, so or worse than other. So this way there are challenges in this area to work on. There are still research going on. So I will be now happy to take questions from the audience if you have. Am I audible?
Yes, sir.
Yes, sir. Yes, sir. You're audible.
Yes. If you have any question, although everyone may be very hungry and also angry.
Thank you, sir, for this insightful session. So I have a question, sir, from your slide number 14.
Slide number 14.
Yes, sir.
Just a minute. You just tell me the question.
Actually, so where you have defined a probability by writing Fi by summation Fi, we generally know the probability is the ratio of two numbers. So Fi means the frequencies must be some integer value, but you have used a fractional value. how it is possible.
Slide number 14. 14.
14.
Just a minute. I'm sharing again.
Oh, sir. Yes.
Slide number 14. Is it rounded wheel you are saying? Rounded
Yes.
wheel selection.
Yes, sir. Oh, in the slide of genetic algorithm,
This one.
it's not visible.
Still not visible?
Yes, sir. Visible. Yes, sir. This slide.
This one.
Yes, sir.
What is the question, please?
Sir, here you have written the probability is equal to Fi by summation Fi.
Probability or the area what it covers in the wheel is actually this is the Fi divided by the cumulative sum. Fi is the fitness value of a particular ith chromosome, and for all I, what is the cumulative value? So this the division is the area, what the amount of area what it covers. Here maybe it is not actually probability.
Yes, it is
Yes.
the proportion of the areas.
Proportion is a better term. Yes, yes. Thank you for this suggestion. Yes, I appreciate.
Thank you, sir. So thank you for giving
Thank you
us
so
your
much.
time, your valuable time, sir. Your session is really very good and very informative. So we'll hope we'll get you later also. So thank you. Thanks all the participants.
Yes, I will be very happy to discuss these things further. You can email me. You can call me.
Okay, sir.
And when if you organize any event offline in person, I will be
Yes,
happy
sir.
to come and meet you all.
So we are planning for such type of program, sir. Obviously, you will be the called for that program. And we also thank our participant to giving us that much time. So we'll meet again at 2:30. So please be with us. Thank you.
Thank you, sir. Thank you, everyone. So I am leaving.
Yes, sir. You can leave.
Thanks.